Hi, my name is Sean McElvogue, and today I'll be introducing to you Lazer Pong, Group 1 submission for the ECE Senior Design Fall 2023 Project Showcase. The motivation behind this project was to design a beer pong-inspired arcade cabinet that is more entertaining and more accessible than current electronic arcade cabinet designs are for this game. So here is the final project for this. The final design was to implement an LED surface display that is individually addressable to display intelligent and entertaining lighting to the player, and then a laser grid along the surface to track the position of the ball anywhere along that surface. This will be used for score tracking as well as positional information anywhere along the surface of the ball. So before we get into the design, here's our group. Matthew Brislenn and Jeffery Cain are photonics specialists who are in charge of the surface itself as well as the laser sensor grid. And then our electronics specialists were Michael, Kyle, and myself, Sean, who implemented the controlling electronics and power electronics. So the way that this table is meant to work is the electronics will run a game program for beer pong, and it will display that game program and game state to the player using the table surface. It will then track the position of the ball when scores are made or missed using the laser sensor grid along the surface. The impressive lighting should have has dynamic effects that will entertain the player as well as inform them along the game state. And the entire project was implemented over half of a traditional beer pong table to make the project more achievable. Our requirements and specifications are listed here. The one I'm going to highlight that will be demonstrated at the end of this video is our overall response time, which needed to be less than a quarter second in order to provide a truly tactile experience to the user. So our first major component, the surface display, is going to be introduced to you by Matthew Brislenn.
Hello, my name is Matthew. With this LED display that we created, we're going to be using LED addressable lights, as well as a grid that will isolate each pixel. And then on top of all those is a clear diffuser panel that will soften the light for the user. Here is a couple different LED light strips that we use, but the one on the right, the fairy string light, gave us the most flexibility when looking at the space between each LED. Here's the diffuser panel to diffuse the light, soften the light, and spread the light evenly for each pixel. And here is the build of the LED surface. So I created a grid for each pixel, and as well as laid the LED strip in a snaking pattern to make it easier for the LED addressing.
And for the next major component, Jeff is going to talk about our laser sensor grid.
Here we have the IR laser transmitters that were considered for the design, and the chosen laser diode was the Cube by brand, as it's very cost effective outside the range of visible light, and also comes with an adjustable lens for collimation of the laser. In this slide, we have the IR receivers that were considered for this design. The chosen photodetector was the Decardu brand detector, since it possessed all of the necessary features that we needed for it to communicate with the laser, as well as it had a built-in amplifier, which would be required for the photodetector to communicate with the MCU, because without it, the voltage generated purely from the photodetector is too small. With these two diagrams, we demonstrate the basic function of the laser grid, in which there is a constant optical signal being sent and then received by the photodetector, as seen on the left side. And on the right, we can see that when the ball is on the table, it will block this signal, and that information will be sent to the MCU.
And for the next major component, Kyle is going to introduce our power design.
All right, so here is a bunch of power supply units. The one that we chose was the BTF Lightning switching power supply. It's the same brand as the lights, so we wanted a 5-volt output for those lights. And the current as well is important to note at 30 amps. This is more than enough for every major component. Here is also our regulators for power. The one that we chose was the Texas Instruments LM317T. We are interested in the input voltage range. It's going to take in the 5 volts from our power supply, and it should output around 3.3 and 3 volts. And our current is pretty high as well, more than enough for both components. And here's a high-level block diagram for our power supply distribution. As we can see, everything comes from our main power supply unit and everything is wired in parallel to that. So everything receives the same current as well as the same voltage. And as final checks, our supply is able to generate 30 amps at 150 watts for maximum power output. And our requirements meet those requirements at 21 amps and around 94 watts.
For the next major component, the controllers were designed by myself. Our controller setup is to have a sensor relay controller, which is the PCB that we have designed, shown here. This houses the power electronics described by Kyle, as well as inputs from all of our sensors. The inputs go into the microcontroller, which then multiplexes them and identifies where breaks are on the board. And then using SPI here at the top of this device, it communicates those breaks to a separate device, an Arduino. The indexes of those breaks are sent to this Arduino via SPI, and this Arduino then processes that to game state data, which it then figures out how that translates to graphics on the surface itself. And then using a single line and a pulse width modulated signal, it communicates to the addressable LEDs what graphics should be displayed. This method was used because the lights are only programmable via Arduino. Unfortunately, our bespoke electronics could not program the lights. It was necessary to have this Arduino device as a go-between. And then for our part selection, we had to pick a microcontroller that was big enough to fit all 48 sensors from the table. And this STM32 device was both well-rated and affordable for a device with that big of a package. So we went with it. And then finally, Michael is going to go over our software.
So our main considerations for the software are to reliably convey all the necessary information to the user, as well as to allow for fast communication between the MCU, LEDs, and laser receivers in order to accurately track the ball. The software block diagram is fairly straightforward. It begins by initializing the clock and GPIO pins, and then begins polling for breaks in the receiver signal, indicating the location of the ball. Then the appropriate routine is completed depending on the location of the break, such as scoring a point. These are some examples of the user interface. The communication between the lasers and LEDs is used to operate the interface like a touchscreen. The user will touch the surface of the table in the location of the menu option, which will trigger the appropriate routine.
Next, a demo of our final project will be shown, along with a specification demonstration for our response time.
So this is the power supply that will be powering the laser Pong table. And once we plug it into the wall outlet, you'll see it comes straight to the start screen. And then if we touch on the start menu, it will start the game. All right, and here we can see that player 1 is selected and has 0 points. And if we press on the green button, we can switch to player 2, who also has 0 points. And then in the scoring cup over there, if we add a score, it'll show a little graphic that says that you've scored. And then we take the cup away and we press the green button again. We can go back to the player select and we see that player 2 has a score. Here we can see that player 2 has 8 points, and if we score again, we'll get up to 9. And then one more score. Game over, player 2 wins. And then from here, it should restart from the start screen again to start a new game.